Yep. Thanks everyone for coming out so late. 6 to 8 p.m. is a very late class. But yeah, so for like a bit of an introduction, my name's Henry, and I'm actually an undergraduate domestic student, kind of like a senior undergraduate student, you can say, going into my 5th year. I'm a civil engineer, but I've taught 1300 once before in term 2 of last year. It's last year now. Yeah. And yeah, I contacted Dr. Eugene, and she was happy to get me on board. So here we are. So I hope I can give some insight on this course regarding how it kind of feeds into the rest of your courses, because it's a pretty fundamental course for most disciplines in engineering, like mechatronic, mech, civil, and mining. I wish I could give more examples on mining, but a lot of the examples which I will be giving throughout these tutorials will kind of be from a civil engineering perspective. But yeah, hopefully bear with me with that. Yeah, so I've got a bit of a lesson plan here. So the first thing I would like to do is start with a quiz, which, for those who don't know, it's basically like a Kahoot, but Kahoot nowadays, you can't have more than 10 people join, so I don't like it anymore. It's like a premium feature. Then we're going to be talking, I'm going to do a bit of a theory overview, because sometimes the lectures can be a bit overwhelming. Like if you sat in the lecture earlier, and there's a lot of pure physics, I like to think of everything from a very practical point of view. So if it helps, it will give you a better understanding of how to solve the questions rather than the deep physics behind it. And then we'll do, there's only 4 questions. It's going to be pretty short shoot. It should be pretty chill. We'll have a break and everything. So that should be good. Yeah, I guess the first thing I'll start with is going to be the quizzes. Okay, wait, let me just check there's an option here. Okay, shuffle questions is off. All right, so if everyone could just join this for me. It's got a QR code, I think. Show QR code. Yeah, you can just join on your phone. It's really chill. It's just a couple of questions to do with theory. Even if you didn't have time to attend the lecture earlier, you can kind of guess the answers. Everything's mostly theory related. Yeah. And hopefully the people online, hopefully 1, you can hear me, and 2, you can join it. It's a good sign. Sorry, let me just check the chat real quick. Yeah, I assume there's no problems online, hopefully. Angle the camera up so you can see. All right, everyone in? Good? Need more time or anything? All right. All right, cool. So I'm gonna start the quiz. Oh, sorry, I think we've got a few more joining. Did you want to scan it as well? Yeah, it's up to you there. Sure. All right, I'm gonna get this started, I think. My goodness, I'm turning that off. I'll try the music again, but we'll have it quiet. We'll go over the answers after, by the way, once everyone's kind of gone through it. I think most people done. I'll just give everyone like 15 more seconds or something to go through this. Alright, I'm gonna end it. Actually, what I'm gonna do, I'm gonna start recording on Teams. Alright. I'm gonna end the quiz, guys. Congratulations, Paddy, Joachim, and Luke. Sorry if I mispronounced anything. Very good. Congratulations. We're gonna do an animation here. All right. So yeah. Wait. How did people even get? Was it shuffled? Maybe I set up the quiz wrong. But like, I saw there was some questions where it was impossible to get it wrong. But anyway, sorry. Let's have a look at the questions. Right. This is 17 and incorrect. Oh my goodness. All right. Hopefully everyone's feeling okay, not too stressed out. I mean, yeah. I can't believe there's incorrect answers for this. All right, so we've got 5 people with civil engineering here, 6 mech, 7 mining. Makes sense. It's a mining course. And then actually 10 people from another engineering discipline. So actually, I'll keep that in mind for like my examples and everything. I'm kind of curious to know which other engineering disciplines this is, but maybe in the break or something you can come up the front and ask me questions and let me know and stuff. All right, next. Yeah, so this is really good. Pulling on a rope is an example of tension force. We'll get into this later, but this is like my favorite example on how to memorize what tension is. So tension is just all about pulling. So something like a rope, something like a cable. Yeah, you're gonna see what that means a bit more later on, but if you got it right, you got it right. Next, a column, right? A column like my drink bottle here. If it's supporting a roof, it's gonna be squashed down. So tension is basically the opposite, compression is basically the opposite of tension, right? So it's things being pushed together. So that's compression. Yeah, so there's actually 2 correct answers here for the unit vectors one. So what I'm going to do is go to my little, this is my Samsung tablet, right? Like an iPad with Samsung. Essentially, unit vectors, right? Was this covered in the lecture? Is this, yeah? Okay. They're kind of like building blocks. So one direction horizontally to the right is the I direction, and then if it's -1, it's going left or in the negative horizontal direction. and 1 in the up direction is the j direction, and then down negative j direction, right? And so what we mean by orthogonal is that they're like 90 degrees from each other, and with the fact that they're 90 degrees, you can basically create any 2D vector, right? Which will be useful for when we're like dealing with forces, which we're going to be dealing with this week, and for basically the rest of the course. And the other note I have here is it's useful for solving relative vector questions later on. So you'll see that especially in like rigid body motion. Yeah, you'll see that you're going to need to learn unit vectors at some point. But like for the next few weeks and leading up to that, they're not going to be super key. Okay, so yeah, this one's interesting. So basically, Pythagoras theorem and inverse tan rise over run. We'll see those formulas as I'm describing them in the next section here. But sine and cosine rule. These ones are all about finding like in a triangle, angles and the side lengths of a triangle, right? That won't be super relevant until rigid bodies, which is like I guess a 5-week course, right? It's probably like week 4. Yeah, week 4 or 5. Yeah. Right, cool. Does anyone have any questions right off the bat with any of that? No? Cool. Let me just check online. Some transcripts. Okay, I think we're good. All right, thanks for participating in that little quiz there. All right, so by the way, at the halfway point, we'll have a break and I'll take attendance then. But with the attendance form, it's going to be like a Google Forms with a QR code. But I'm also like, you can put down your email optionally, and I can send you my notes. So feel free to take notes or not. It's really up to you. If you like my notes, then no need to take my notes. So if you can just type down a couple of things if you have questions, and then the best time to ask them, I suppose, is like the mid lesson break. And then, yeah, then you'll remember to ask me whatever. Then. All right. So cool. First, we're going to go over a little bit of theory. So the first thing's forces, right? So forces is the focus this week. And we'll touch upon moments in the next... Oh, sorry. Excuse me. I'm used to saying weeks because I taught this in term 2 where it's based on weeks. But what I mean is today, because you got another lesson tomorrow. So the focus of this lesson today is going to be forces. And forces are a vector. So I'll give an example of something that's not a vector, right? So from physics, something like mass is actually a scalar, where it's just got a magnitude. And yeah, the units are going to be kilograms for that. Vectors, on the other hand, like force, right? They've got a magnitude and a direction. So, yeah, everyone's done Physics 1A. You should, I guess, kind of have heard this before at some point. But yeah, that's the first thing to note about forces, and you'll see how that plays into the rest of this. The other thing to note is units. So sometimes forces will be given to you in newtons, and sometimes forces will be given in kilonewtons. Yeah, it's 1,000 newtons in 1 kilonewton. So that's the conversion rate. Okay. Let me just paste this down. Oops. Okay. So basically, there's 2 ways to express forces, essentially. Generally, we stick with the first type, which is you can express it in terms of a magnitude and an angle. Angle is usually denoted by theta here, and magnitude is usually denoted by the letter of the force. Here is F in these what are they called? The straight line thingies, absolute values. Yeah. And how it would look when drawn out is something like this. So that's a XY plane. And you've got your magnitude and you have the direction it's coming off of. So when you're answering a question about like find the magnitude and angle of this force, that's what they're asking for. They're asking for this and this, right? Okay. Next, there's also the unit vectors, which I touched on a little bit earlier. So the I direction is the horizontal direction, and the J direction is the vertical one. I don't think there's any questions in this course which has K. So K would be like a third dimension if you want to add in a third dimension as well. But yeah, so here's how you might be able to express a vector, which is a force in unit vectors. So here I've written out like very thoroughly. So I've got a little hat for vector notation. I've got the units as well. But essentially, you can break it up into Fx and Fy. That's just like the force only in the horizontal direction and force only in the vertical direction, right? Yeah, so it'd be 1,000 up. Actually, I'll just write. Sorry, 1,000 to the right. And then 400 down. And then this is F, right? So, just get on my notes. Yeah, in terms of converting between these, so every now and then you'll find yourself having to convert between these notations. And we use the formulas which I mentioned earlier, which is Pythagoras and inverse tan rise over run to do this. So getting from Fx and Fy, right? We can use this formula to get to theta. So that's tan inverse rise over run. That's the way I remember it. Rise because, yeah, and run because that. All right, and then to get to magnitude, use Pythagoras. Right, so that would be the other formula. Every now and then, you also have to convert the other way around. So once you have the magnitude and the angle, say you want to get Fx or Fy. See if I've got space for this. You'll have to use trigonometry, right? Yeah. Just be careful as well. That's a good color. I'm doing red. Just be careful here, right? Because this isn't always the formula. It depends on like what your angle looks like, right? That's a good put. Sorry, this is an aside. You guys remember unit vectors back in year 9? Sine, cos, tan stuff. So if you have your sorry, not unit vector, unit circle. Yeah, you have your unit circle, and then yeah. So you have these arrows, right? That represent vectors. These angles here, I don't know, it's kind of a stupid name, but I call them the butterfly angles because it looks like a butterfly, right? So when I say the angle equals tan inverse rise over run like this, what I mean is you get this angle, right? Because every now and then you might get tricked because you might be looking for this angle instead, in which case you use this, which is just swapping it around, right? Yeah. Does anyone have questions to do with that? No. Online all good? Okay. I also just want to quickly talk about resultant forces. So here we have a pin support or something where there's 3 cables that are pulling this tension off of it, and it's all from the same point here, right? So to get a resultant force, what you can do is you can sum the x forces and you can sum the y forces, So yeah, say they give you some angles for this, right? Yeah, you would use like sine and cos. You'll see that in the worked example, the first worked example, right? But there's essentially two ways to express it in the way that we were talking about earlier. So if we call the first way 1 and the second way 2, like the unit vector way 2. Yeah, for the first way, you just use your Pythagoras to find the magnitude and to find the angle. Go like this, tan inverse right over run, right? And if you want to express it in unit vectors instead, Rx is our horizontal component, and then it has I unit vectors, and then Ry is our vertical component, it has J unit vectors, right? That's pretty much resultant forces, right? Any questions so far? Okay, cool. Next I want to talk about axial forces. So before, when I was talking about tension on a rope and like compression on a column, what I mean is, it looks like this, yeah? So essentially tension and compression are opposites of each other. And they come in a pair of forces, except due to Newton's free body diagrams, like, for example here, these are cables being pulled away from like a node. This is in tension because it's being pulled away from the node. So I guess it's not like a pair of forces in every like free body diagram representation. Yeah, sorry, I don't know if that's the best explanation, but yeah, essentially these are axial forces because, for example, if this is a beam, if these are beams, right? This would be the axis here, right? And axial forces act along the axis. So for tension, they're pulling away, and then compression, they're pushing in, right? Yeah. Okay, cool. That's basically all the theory I had to go over at the start of this lesson. Now I'm going to move on to the work solutions. Don't think we've got any questions in chat. Okay. Yeah, okay. So for this first question here, we have this free body diagram that's part of a building. And essentially we have two forces acting along here. This one here is compressing our beam, sorry, not beam, our member. This thing, we can just call it our member. And here we have a tension force pulling away from it, right? You'll learn on Friday that this structure is part of a truss, or could be part of a truss, because trusses use axial forces, right? Like axial forces act along trusses. Yeah, you'll find that out later. Okay, so we have an angle here for this member on the right, but over here on the left, we have this kind of representation of geometry. So yeah, because 3, 4, and for a Pythagorean triangle, this one would be 5. This is like a pretty common representation of, how do I say it? Yeah, you'll see, like in my working out, like you don't really need to use sine and cos here. You just need to use, so if you want the horizontal component, you can just use the horizontal part divided by the hypotenuse, and that gives the same thing as sine this angle, whatever, right? Yeah. Yeah, anyway, so what the question's asking for is it wants us to find the resultant force at point O here based on its external loading, which is these two forces, right? So we're going to take the sum of the forces in the x direction, and that's going to give us Rx, which is the resultant force. And so if we're looking at our compression force, it's acting to the right. We're just looking at the horizontal components of these forces. And if we look at our tension force, it's also acting to the right. So both these parts are going to be positive. And I'm going to take the magnitude, which is 3 kilonewtons, and take 3 over 5. So 3 over 5 comes from this over the hypotenuse, right? And then for the tension one, we're going to take the magnitude, which is 2 kilonewtons, right? And we're going to take cosine 30. And cosine comes from the adjacent side of the 30 degrees, because we're just looking at the horizontal forces, right? Sorry if I'm going a bit too slow for some people. Yeah, I just like to go really slow for like the first few questions on that, right? Also, we've got the time, it's all good. Okay, so once we punch this in the calculator, you'll get that Rx is 3.53 kilonewtons, yeah? Okay, we do the same thing in the y direction here, and we're gonna find out what the resultant vertical force is. So the difference here is that the compression force is acting downwards, whereas the tension force is acting upwards. Remember, we're just looking at the vertical components of these two forces. So that's going to mean that we're going to have a -3 for the magnitude. And we take 4 over 5, which is the vertical part, right, divided by the hypotenuse. And instead, we have 2 sine 30. So, yeah, that's this part here. It's the opposite side, right? All right, so we get Ry is -1.4 kilonewtons. All good. So let me just draw out kind of a visual representation of this. So now, essentially, we're solving for this diagonal, like this hypotenuse, right? R, which is the resultant force. And we also want to know what this angle is, right? So you can see where this is going. So R, we use Pythagoras. That's Pythagoras. And for theta, which is the angle, we can use tan inverse rise over run. Yep. The other thing to note about the angles here is here I've decided to represent the answer in a negative angle, but you can either do this, or you can say, we can erase that, and you can say down from the horizontal, or you can say like decline angle or something like that. It's, yeah, essentially the same thing, right? And yeah, that's the first question. Any questions to do with that one? I'm actually going, like, there's only 4 questions, so I'm actually going faster than I expected to. So what I'll do is I'll give you a break now, and then we'll do the last 3 questions after, yeah, the break. So I'll give you 10 minutes, just chill out, 5-10 minutes, yeah. If you have any questions, feel free to come up the front as well. I can answer them. Oh, sorry, here's the attendance form. Yeah. Let me know if it doesn't work. So yeah, apparently if you come to 90% of the classes, 5 marks, 5 bonus marks or something like that. How good? I just found that out 5 minutes before the shoot. So yeah, if anyone's listening to the lecture recording, this link won't work. I think it's going to close off after the shoot finishes, so please fill it out live, I guess. Oh yeah. Yeah. Oh yeah. Yeah, it's a bit harder. Because I guess statics is like the first half of the course, and statics is things that don't move. So naturally, they're going to teach you things that aren't moving first.
Right.
Yeah, and then later we're going to move into.
So it's dynamics, just like velocity.
I can actually like give a little bit of a like intro to the difference between them after the break or whatever. Just a few more minutes. I think some people online might just be going to the bathroom or something, and then
Okay.
yeah. Right, but your question was is dynamics things that like we like to do with velocity? I mean, like the short answer is dynamics is like a pretty broad topic, but essentially, how do I say this in as few words as possible? Yeah, like. Okay, so I'm not doing a very good job off the top of my head. I'll think of an answer in like 1 minute, and then I'll just draw it up. It should make more sense. Yeah. Okay. All right. We're just gonna continue with the shoot now. All right, everyone online. Hopefully you're back. I don't know. Send a message in the chat for online people if you missed the QR code. All right, so I'm just gonna answer 2 questions that I got over this break. The first one is on triangle, like what I meant by the triangle ratios from earlier. So, what was it? Here, right? So I'm just going to redraw that truss, that member. I think it looked like this. All right, so essentially we're only looking for either the horizontal component, or the vertical component, but we only know the diagonal kind of magnitude, right? And so we want the ratio, like we want the proportion of the diagonal, which has like a weighting of 5, I guess you can say, and the horizontal one will have a weighting of 4, and the vertical one will have a weighting of 3. And so when we're taking the magnitude, so let's call it Fx, right? The horizontal force. We're just doing 80% of the diagonal, right? That's essentially one way you can think of it. When we're taking the vertical one, we're essentially doing 60% of the diagonal. So why that triangle ratio works is because it's going to be some portion, like some ratio less than 1, and you're multiplying it by whatever magnitude this vector is. If that makes sense. Yeah. Send a message in the chat if that didn't make sense or whatever as well, and I'm happy to continue. Wait, I didn't check the chat. Oops. Can you replace 3, 4, and 5 with any numbers then? Yeah. So another example. Wait, let me just check these are the right numbers. I'm pretty sure it's 5, 12, 13. Yeah. So 5, 12, and 13 is another Pythagorean ratio that you'll see very often because they're like just whole numbers. But it's because if you go like this, I guess, the left-hand side equals the right-hand side, and it just happens that those whole numbers work well with each other. Yeah. So if you want to get the horizontal proportion, you go 12 over 13 of whatever this magnitude is. And if you want to get the vertical component, you go 5 over 12, right? And so this is just some number less than 1, and you're multiplying it by the magnitude of the diagonal. Oh, sorry. Oh, no. Sorry, wait. Okay, my bad. So that number works, that 5, 12, 13, that's another triangle that works. You can do it with numbers which are like decimals as well in that triangle, but like it's usually only convenient to do it when the whole numbers. Otherwise you'll usually just see it represented in terms of some degrees, like whatever degrees that is. Yeah. Yep. No worries. Okay, and the second question, I'll just give like a kind of introduction to dynamics. So what we're doing right now, I should have started this, is statics, which is just things that don't move essentially. So Newton's first law here's how I like to summarize it. It's kind of a lazy way of doing it. Sum of the force is 0. It's just like static equilibrium. So it's called static equilibrium. Yeah, it just means that there's no acceleration acting on the system, and this is kind of the basis of statics, right? And yeah, that's like, and the reason that's comparatively easier is because Newton 2 is sum of the forces equals ma. So this just introduces so many like new problems, right? Because if what you're dealing with is moving, it has like this acceleration, and then the acceleration adds like a time dimension as well. So yeah, and yeah, it just gets into this whole rabbit hole. But essentially, how the dynamics portion of this course is going to be broken up, you'll see in like the later few weeks, is this. Right, so there's going to be particle particle dynamics, and then rigid body dynamics. So particles are like, you pretend that they don't really have. I guess everything happens off of like the center of gravity of a body. So you can pretend that like this is like a billiard ball or like a pool ball or whatever, and all of your calculations will just be based off of its center of mass, so just the middle. And yeah, that could be moving, that could be doing whatever in that question. But the difference is a rigid body. It could look like that or something, right? And then here's its center of gravity, which is called G. And once it has like this kind of shape in 2D space, or even 1D space, so when I talk about beams in the statics portion of the course, that's actually a 1D rigid body. Yeah, rigid body just means that it's not a single particle. It can have like bending moments acting on it. It could, yeah. It has like some dimensions to it, right? Sorry, I'm kind of yapping, but like, there's also kinematics for both of these, and kinetics. And then there's work, energy, momentum for these as well. Yeah, that's kind of how the dynamics portion of this course is broken up. Yeah, again, if you filled out that form and you put your email down, I'll just send you these notes. So yeah, I'm gonna quickly check the chat. Okay, I think we're okay. All right. Is everyone all good? Or yeah, if you got any more questions, raise your hand or whatever. Otherwise, I'm gonna keep going. Let me get my notes here. All right, so let me zoom in. This question, right? There's a spike in the wall. It's connected to like some timber wall, and yeah, this is kind of a weird question, to be honest. So what's happening is there's some unknown force P pulling like some tension force acting kind of like up and right, and then there's like a known tension force acting down and right. But also there's this like weird obstruction here, which is called the block A. And the idea is like this barely doesn't obstruct it. So that's going to help us find out angle for this for these forces. And also there's like this reaction force here, called T, which is kind of an unknown that we're going to have to solve for. So essentially in this question, there's two unknowns. There's the tension into the wall, and then there's P, which is an unknown external force that's pulling up and right, yeah? So, okay. The first part of this question, which is kind of weird, is that this obstruction thing, we're going to have to find the angle first that makes it so that these barely aren't obstructed, like these two ropes. And then after we do that, we're going to find T and P. And essentially, we have two equations that we can utilize. Sum of the forces in the horizontal directions is equal to 0, and sum of the forces in the y direction is equal to 0. So this is called static equilibrium, and it's saying that in order for this thing to not move, like this whole system not to move in this free body diagram, like the sum of the forces have to equal to 0, including the reaction forces driving this spike into the wall, right? Anyway, so first thing we're going to do is find the angle, right? Theta 1 and theta 2, which I drew earlier. So let me just redraw that. Okay, let me just show you where I got those numbers from. So this block, I guess this part of this block is 100 millimeters up like that, and then it's 200 mils away from the spike's center, or like the circle bit in the spike. Anyway, so we're just going to use 10 inverse rise over run. We get that. And, oops, sorry, getting ahead of myself here. I'm going to redraw the second angle as well. Okay, so angle 1 is theta 1 and it's going up from the horizontal, and angle 2 is theta 2 but it's going down from the horizontal. I've decided to represent both of these angles as positive angles, but we'll just keep that in mind in our calculations. It's fine. Okay, so the next step is we're going to use force equilibrium here. Okay, oh, sorry, spoiler alert. So we know that the sum of the forces will balance out in the horizontal direction and in the vertical direction. However, there's a correct order to do this. So you can either take the sum of the forces in the horizontal direction first or vertical direction. So which one would you do? Let's have a think about it. All right, so answer is you have to take it in the vertical direction first. And the reason for that is because if you analyze the forces going vertically, right, there's only going to be one unknown, which is the vertical component of P. Whereas if you analyze it in the horizontal direction first, you're not going to know what P is and you're not going to know what T is, right? So you're going to have to like backtrack and then keep going, right? Yeah. So we're going to analyze it in the vertical direction first. Okay, let me just I might just redraw this so it's easier to look at. Number 1.6K. Okay, here it is. So we're going to do P sine this, right? So what I've done is I've decided, well, not that I've decided, I have to use sine here to look at the vertical because we have this butterfly angle, right? I guess. And sine represents the opposite, which is the vertical component, right? And so I've done that for both these, and I've made sure to include our negative for the force going down. So when we rearrange this, we get that P is 2.146, right? Okay, next, now we know P essentially, right? We're gonna do the sum of the horizontal forces in static equilibrium. And we can see that we have negative T, because it's going to the left, plus P cosine 26.57, plus 1.6 cosine 36.87, right? Since we know P, I'm gonna replace that with what we worked out in the last bit. Now we have to just move T to the other side, make it positive, and then chuck this part in our calculator, right? And that gets that, right? So now we've solved the question, I think. Yeah. So, don't have any questions with that? Yeah, this is a bit of an unusual question, I'll be honest. Like, this block thing is really weird, but yeah. Yeah, cool. So, there's a bit more theory now, but I'll explain it as we do the question because it's just easier than explaining it separately. What's happening here is that there's some force acting diagonally onto this slider, which is free to move this way. We call it the tangential direction, right? But it's resisted in the normal direction, so this way, yeah? But everything's kind of at a weird angle, and sometimes you'll find it advantageous to find the sum of the forces not in x and y, but in the normal and tangential planes, right? So the normal and tangential planes are always orthogonal. Is that what I said earlier? Yeah. They're always at 90 degrees from each other, right? So it's very similar, but you're just gonna have to like do it from a different perspective, essentially. So what I'm gonna do, just because I don't know, I think it'll help with the explanation here. So I'm gonna redraw it from the XY angle. Oh, not really from the XY angle. It's as if I like tilted my head and looked at the question. And this is kind of the XY plane now, like we've just tilted it slightly, right? Okay, so one thing you have to note is how these angles work. So this force is actually coming at the tangential plane at a 30-degree angle, oh sorry, a 40-degree angle, but we know that because the slider's at a 30-degree within the block, right? So actually, this angle here is going to be 40 degrees added up, right, from the tangential plane, right? So we're given that the tangential component of the force is equal to 75 newtons, right? And we know that this number, the tangential component, is the diagonal cosine 40, right? We're just like, that's just the horizontal component of our diagonal. So we can kind of reverse engineer this and replace that with 75. Now we're just solving for the diagonal, right? Because that's the part we don't know. And that's equal to 97.91, right? So now we started with this one, and then now we've pivoted to that one, and last we're going to solve for Fn, right? So that one's not too bad since we are used to doing it having known the magnitude of the diagonal. So we're replacing this f with 97.91, not 75, right? And it's a sine part because, like we said, it's a vertical part, right? Vertical from this perspective, right? Yeah. And then so Fn. Oh wait, no, I already wrote that. Okay, cool. So now we've solved for f and the normal component for this question. Yeah. Anyone have any questions? Yeah.
What does it mean by tangential component?
Yeah. So, okay, essentially, I don't want to like over-explain the answer to this because we're gonna move on in like the next few lessons to when we look at rollers and stuff. So essentially, inside here we have this slidey bit. I'm gonna try to draw in 3D. We have this slidey bit, which is free to slide like up and down, right? So that's actually called the tangential direction. Yeah, and then but it's resisting in the normal direction here. Like there's a reaction that's happening due to this force. Yeah, in the normal direction. Hope that makes
So we
sense.
haven't covered this yet.
It's kind of weird. The workshop questions, like they want to have like a diverse amount of questions so that you can understand a bunch of different concepts, but they jump ahead sometimes.
Okay.
So we haven't fully learned this yet. You'll learn about rollers and stuff later. A more common roller is like, okay, pretend that's a beam, like going to the right over there. We don't really care about that. What we care about is it's on wheels, pretty much, and that's an example of a roller. Because what happens is this support, it's called a support. It has a like vertical reaction if this is a beam that's perfectly horizontal. However, it won't have like it's free to move left and right. So I guess like yeah, this is like a normal force. I don't know if that's the right word. Yeah. Anyway, sorry. The normal and tangential notation is relative to kind of like an incline or a surface, right? Yeah, if that makes sense. Yeah. So if it's completely flat, the tangential direction is just horizontal, and then the normal is vertical, right? Coming off the surface. If that makes sense. Yeah. Okay. Do you have any other questions? Let me just check online as well. Okay, cool. Cool. We're gonna move on to the last question here. Okay, so the important thing to take out of this question is friction, right? This is like a rope or something, and it's being pulled, and it's being pulled on like it's pulling a block pretty much, right? Which is sliding along the ground, and we know two constants here. We know the static friction constant, and we know the kinetic friction constant, which is the one with a K, right? So static is S, K is kinetic, right? Yeah. So I just want to talk about friction a little bit first before we like head into this question. So why this is a static question is because it tells you at the start that the block is stationary, right? And it has to overcome some amount of, there has to be some amount of force applied to it before it starts moving, right? That's what we call a slip, right? So see this word used every now and then. So when it's not slipping, you can use the static friction, like constant, right? And then when it is slipping, you use the kinetic friction one. So that means it starts to move and stuff. But this question doesn't ask for like, oh, how fast is it moving, whatever. That's like the dynamics part. All we care about right now is Actually, well, we care about the magnitude of the friction force, but okay, anyway, I'm just gonna dive into this, right? First thing I'm gonna do is redraw this in a free body diagram, just to make it a bit clearer, I guess, on what's going on. Okay, so we have this block, and this should be kind of familiar to you guys from physics, or like high school physics or whatever. So it's just got some weight, and the formula for weight is gonna be mg, right? And then there's a normal force. So actually normal force acts from, so the weight force acts from the middle of the block, right? If we want to draw it perfectly. But the normal force actually acts from the surface, right? It comes off like this. However, mathematically it's the same as if I drew it from the middle of the block. Because you'll find out in the next lesson this is the same line of action. Or maybe you heard of that in the lecture already. Line of action's like it's in the same direction or path of the arrow. So yeah, anyway. So that's a normal force. And then we have our friction force. And we have the rope pulling it at a 30-degree angle. Okay, so right off the bat, we can usually calculate the weight quite easily because we know that it's a 100 kilo block, and we assume in this course gravity is 9.81, right? I don't even need a calculator for that. Is that right? Okay. You basically always need the normal force to calculate the friction force, right? So when you're deciding whether to do the sum of the moments, some of the forces in the vertical or the horizontal direction first, you want to think about how to get your normal force first before your friction force, right? So what I'm going to do, I'm going to take the sum of the vertical forces, and so this block, it's not moving up and down, right? Like, how do I explain this? Yeah, there's this rope pulling it diagonally, but it's still in equilibrium because it hasn't like suddenly been yanked and like it's gonna fly upwards or whatever. It's just like a gentle pull, and so when it moves or doesn't move, it's gonna stay in static equilibrium in terms of up and down, right? So it's gonna be sum of the forces in the y direction is 0, and so all the upwards facing arrows, like n, you can do upwards, and the downwards ones, like weight, gonna subtract it, right? And also, we're gonna add the vertical component of the diagonal force here. And when we solve for that, we get n is this, right? Okay. Oops. All right. So before I calculate the sum of the horizontal forces, right, I'm going to try to explain a bit more about the friction and the slip, okay? First, we want to calculate what the maximum friction before like slipping occurs is, and then we're going to check whether it surpasses this number, pretty much, right? Okay, so here's a formula. I denote it like this. I think the answers might denote it slightly differently, but so this means force static max, right? So the max before the static friction actually becomes kinetic, like it starts moving, right? And so this coefficient, we're going to use 0.8. And for the normal force, sub in the normal force which we've worked out, right? So the max it can be is 505 newtons, right? Okay. now we're gonna do the sum of the forces in the x direction, right? So because the question told us, right, the block is stationary before the force is applied, what we're gonna do is do the sum of the forces is 0. And so, yeah, like just pretend this rope, right? It tugs on this block and like keeps tugging, and at some point it's gonna move, right? But we're checking whether it moves or not. So we're gonna start with the assumption that it doesn't move, and if we're wrong, we're wrong. Okay. So that's why we're doing sum of the forces is equal to 0, pretty much. So what I've done is I've called this friction force FF, because I don't know if it's static or kinetic, so it's fine. I'll just calculate FF. Oops. Right, and then when we solve for that, this is equal to 606. Right, so because this force is greater than fx max, fs max, right? What's happened is it slipped now, right? And now we have to recalculate the force because the question is actually asking for determine the magnitude and direction, I guess, of the friction force, right? So the friction force actually changed after it starts moving. It doesn't, like, this question doesn't need us to calculate how fast the block is moving or whatever. All we have to calculate is what the friction force is going to be from now on since it started moving. So all we need to do for that is we use our kinetic friction constant, multiply it by the normal force, yeah. So we found that our kinetic friction is 379 newtons in the left direction, right? It's acting left because it's opposing our motion. So we don't actually care like about the block's motion. We just care about the friction force acting on it. I'm really going to butcher this because I don't remember it fully off the top of my head, but there is a graph for it. You can look it up. It's called static friction and kinetic friction graph, and it looks something like this. So this is like this is let's say, what was that one? It was called P, right? So essentially what we calculated here at the end is this 379 newtons, right? So it's actually a flat 379 while it's moving, but before it moves it's kind of linear. You can linearly change, right? So here was fx max, which was 505, right? And yeah, it's kind of how it works. And what happened is when we calculated ff under static equilibrium, it was 606, right? Which would have been off the charts here. So it just dropped and became this, right? Yeah, I don't think I butchered that too bad. Hopefully that was that. Okay. Anyway, that's all the questions. Yeah, does anyone have questions right now? If you're more comfortable just coming out the front, happy to stay here for a bit until everyone leaves. But other than that, that's the whole shoot. Pretty short one today. Thank you very much. Yeah, I guess see you tomorrow. Sir? I'll zoom in. Which part do you want me to zoom into? The top of the to the bottom? Yeah, okay. I'll leave it on this for now. All right, everyone online, you're welcome to leave as well. Yep.
I seem to remember from high school that they had one which was rolling, but it still gave appropriate static. Is it always worth checking if it's static or if it's rolling, you just
Yeah, I think I know the type of question about. That comes in rigid bodies, so that towards the dynamics part of the course. And for that, you do the exact same check actually. So regardless if it's a circle or it's a box, you have to check for static first, and if it surpasses the static friction, then it's fine. Or if you're told actually that it's already in motion, it just uses the kinetic friction constant. So that's maybe what you're thinking about.
Yeah, because I remember this, but it probably is a question for people on way
Yeah. If it says that it's stationary, like it starts stationary, you have to check if it surpasses the slip.
Sorry. That's a question. How should we revise for like the midterm?
Oh, when is the midterm, by the way? I haven't been added to the middle yet.
Next week, Friday.
Next week?
Yeah, that's fun.
No way. Actually, so to be honest, right?
Is it like a like 1-on-1 where you just like, do multiple questions and then you get it? Just practice.
So one like kind of thing that I've heard about this course for like the summer term is they don't provide enough questions to practice.
Oh.
This is the workshop questions, but I think Jing's trying to find more questions to practice with.
Right.
Okay, you have to check with Jing. I don't know what's on the midterm, but I assume you kind of want to like know two components of the statics. You want to know how to answer the questions, so it's good to practice. Yep. But you also want to know like the theory behind it pretty well, in case there's any like theory-related questions, like multiple choice, for example.
There is multiple choice.
I have no idea. You have to ask her in the lecture. But if there is, then you'll have to kind of deeply understand things. And to deeply understand things, I would recommend you go to her lectures.
Right.
Yeah, and ask her questions and probe, because she knows a lot more than me.
You've done this course before then?
So I did this course back in 2021.
Oh, okay.
And then I did this course again, quote unquote. Oh, sorry. I did it with the civil school in term 2 back in the day. And then I did it again as a tutor in term 2 last year. So this is my third time taking this course.
Right.
I'm kind of learning as well with you guys.
It gets a lot harder like second half.
Oh yeah. Yeah, I'm not gonna sugarcoat it, man.
Have you
Guess
done,
I
have you done like 1-on-1?
No. It's not required for my degree, yeah.
Right.
Are you doing electronic or something?
Mechanical.
Oh, you guys have to do elect as well.
Yeah, that was pretty hard.
I've heard it's hard.
Yeah,
I've never done it.
you're doing
really,
civil.
so. Yeah.
Okay.
I don't really need
I
it.
see.
Civil doesn't even need physics 1B. So
I haven't done that yet. Is that second year or?
maybe Mac doesn't have to do it. I'm not too sure.
Right.
But we don't have to do elect. We don't have to do physics 1B. All good. Thank you.
Okay. Thank you.
All good now. Yo, what's going on?
So we found that as friction is less than the 700 cos 30 component, we can say that the sum of fx is actually greater than 0. So is the object accelerating towards the right?
Yes.
Okay.
But since we're just dealing with statics right now, we don't really mind like how quick it's going or like the acceleration it's going at. All good. But the idea is, if it surpasses the static friction barrier, then it's moving. Yeah, it's moving to the right.
Okay.
Accelerate to the right.
Okay.
All good. Okay. Thanks for coming. All good. Thanks for coming. See ya. Thanks. See ya.